Let's continue with these integration by parts examples. Remember that we have to pick when we're doing our integral, we pick one part to differentiate, one part to integrate. So here's our example, our next example. One part to integrate. Our very first example that we did was x e to the x. And there we differentiated the polynomial piece. So let's do that. Differentiate the x squared, and we'll integrate the e to the x. This seems like a good choice because if I integrate e to the x, it stays the same. If I differentiate e to the x, it stays the same, but the polynomial will get simpler. F prime is 2x. It got easier. G, integrate e to the x, get e to the x. So now let's put those pieces in, following this. F times g, so the x squared times the e to the x. F times g minus the integral of the two things I made. Minus the integral of the two things. So I made the 2x and I made the e to the x. Now this is going in the right direction if this new integral that we have is easier than the old integral. It is. This was x squared, e to the x. This is only x, e to the x. So it's got simpler by one step. But we're not done yet. I can't immediately integrate this. How am I going to integrate this? I'm going to use integration by parts. So I'm doing this second integral here with integration by parts. So I'm going to have another set of, so I'm just looking at this integral here. I need a piece to differentiate, and I'm going to make that the 2x. I need a piece to integrate, and I'm going to make that the e to the x. So let's differentiate the 2x, and let's integrate the e to the x. Stays the same as e to the x. And now this integral in the middle here, so equals zip. All right, I'm just working on this integral here in the middle. It's going to equal to f times g minus the integral of the two things I made. So I made the 2 and I made the e to the x. I made the 2 and I made the e to the x. So that's parts a second time on this integral here. And I know I'm going in the right direction because this new integral I have, integrate 2e to the x, is easier than the second integral I have here and the original integral. It's the easiest integral of all that we see here. I can integrate 2e to the x. That's just 2e to the x. So we have these pieces. And integrate 2e to the x is just 2e to the x. Notice I'm careful to be inside these brackets because this minus sign is going to carry on all the way through. So if I was sloppy with the brackets, I might mess up the minus sign. Tack on a plus c and I'm done. Every time I did parts, it seemed to knock this power down by 1. It was 2, then it's 1, then it's 0. Oh, here's another one then. And this looks, okay, let's do integration by parts here again. I need a part to differentiate, and I need a part to integrate. The e to the x squared, I can differentiate that, but I think I want to differentiate the polynomial. Oh, this makes me remember one from the previous video when we were integrating cosine x squared. I wanted an x. I wanted an x there when I integrated so that I could do substitution on this part. Remember that last video. So that leaves this with an x squared. I still, when I multiply the f times g together, I still get the x cubed, but I think this is going to work out nicer. So f prime is equal to 2x, sure, and when I integrate this, I'm going to get e to the x squared, and I'm going to get a half out front here. So I'm not doing the substitution out formally, I'm just sort of checking here. If I differentiate this, e to the x squared is e to the x squared times 2x. The times 2x, the 2 is going to cancel, and that's going to leave this x here. All right, so equals, by parts, f times g. F times g. So x squared, f times g, minus the integral of the two things I made. The two things I made are the 2x and the 1/2. Oh, when I multiply these together, that 2 and that half is going to cancel. So I'm just going to end up integrating the 2 cancels, x e to the x dx, which I can do. Let's do this integration. Integrating x e to the, we already did that. That's this half here. That's this plus c, done. That wasn't too bad. Wasn't too bad because we learned from the last, we learned from the example up here how to split that x cubed into an x squared and an x. That's what I mean by, by learning the rest of this integration by parts by practice. There's a lot of these little pitfalls here that we can encounter when we do our practice, when we do our homework. You get overconfident. You think, well, I get the formula, differentiate one piece, integrate the other piece, pop it into the formula, and I'm good. I'll figure it out on the quiz, on the test. There's a lot of little subtleties, little pitfalls that you want to encounter. Well, it's nice and comfortable practicing at home rather than, on the final exam or something. And parts is an important piece. Here's this next example. This next example illustrates, I do integration by parts with this next example, but it's going to illustrate a point here, which we'll see. But I remember doing this example when I was in calculus, which, was a long time ago. But I remember this one from the book. So I see that I want a piece to differentiate, and I want a piece to integrate. But when I looked at this, it was like, all right, so a piece to differentiate, a piece to integrate. I see the two pieces here, e to the x and sine. If I differentiate e to the x, I get e to the x. So it doesn't get any better, it doesn't get any worse. If I integrate e to the x, I get e to the x. So it doesn't get any better, but it doesn't get any worse. The same with the trig. If I differentiate, it goes to cosine. If I integrate, it goes to minus cosine. It's still trig. So none of those two pieces get simpler like did happen with these polynomial pieces. So right now, I don't see any reason to choose one over the other to be the f. So I'm picking the piece I'm going to differentiate to be the sine, and I'm picking the piece I'm going to integrate to be the e to the x. A little bit arbitrary right now because I don't see any reason to pick one over the other. So f prime is equal to, differentiate the sine, I get cosine. Okay, that's no problem. Integrate the e to the x, it's just e to the x. Okay, so do an integration by parts. That's equal to f times g. F times g. F times g, g times f, same thing. Minus the integral of the two things I made. Okay, I made these two pieces, so minus the integral of e to the x times cos x Okay, now I know that the integration by parts is going in the right direction if this new integral is easier than my old integral. It doesn't look easier, it looks it looks the same. E times trig, E times trig. It didn't get any worse, but it didn't get any better. So here's where I remember feeling like, oh, I feel like I'm going around in circles. And you sort of think, if I do parts again, which is the only thing I can think of doing, that's just going to turn it into E sine again for the integral. So it's going to be going round and round and round in circles. But let's proceed ahead. We know how to do integration by parts. Let's just go ahead. I'm going to do integration by parts on this second integral here. So this is my second parts. Now, I need to pick one piece to differentiate. I differentiated the trig. I'm going to choose to be consistent and integrate the e to the x. I'm choosing that because, because now I know how to do it. If you pick the other way, if you decide to switch it up, if you differentiate the e to the x and integrate the sine, what will happen will be your whole equation cancels out to get 0 or equals 0, which isn't wrong. 0 does equal 0. It's just not helpful. So I'm choosing to be consistent. I'm differentiating the trig, and I'm integrating the e to the x. So now these are the f's and g's and stuff for this inner parts here. So that's going to equal to I'm working inside this bracket here. So it's going to be f times g, so e to the x times cosine, f times g, minus the integral of the two things I made. The two things I made are e to the x and minus sine. Okay, well, this is, I knew it feels like I'm going round in circles, and okay, f times g, that's here, minus the integral of the two things I made. The derivative of sine is cos is minus sine. So that's, all right, we can make this a little bit better. Let's take this negative sign, bring it to the outside, and then a negative is a plus. Okay, but here's where sort of I remember my heart sinking, because this, I'm back to my original integral. I'm just going around in circles. Well, here's the trick. Let me take this piece, and I need some space, so let's put it down here. This is what I've got now. Well, what am I trying to do? I'm trying to get this integral equals something, some formula. So just to make my algebra easier, let's call that big I for integral equals. So integral equals integrate e to the x sine x. That means I can replace this integral here with a big I. Now basically, let's move this I over here. This equation, I just want to solve that for I. I equals, if I multiply this minus sign through that bracket, that's going to be minus I. So I equals e to the x sine x minus e to the x cos x minus I. I can bring that I over to the other side. It becomes a 2I equals okay, now I just divide both sides by 2. And now I wanted to see what's this integral. It equals I, and now I've got I equals a formula. Tack on a plus C, and I'm done. So it looks like you're going around in circles, but you're not. You can, if the integral pops up again, you set it equal to I for integral, and then just solve for I. And you can make it, it's almost like we trick it into integrating itself, really. All right, so, and you know, encountering this sort of thing on a quiz or a midterm, if that's the first time you thought of that idea, you're not going to be able to figure it out in time. It's nice to encounter this in your homework. So integration by parts, an important technique. It's important that you do some practice with it as well. All right, that was all the stuff we've been doing so far have been indefinite integrals. We've gotten an indefinite formula. We'd have to tack on a plus c. What about definite integrals? How does integration by parts work with a definite integral? Well, we know that we don't have a plus c. We're going to end up with a definite number. But let's see what we have here for. I've got two pieces, 2x minus 4, that's a line, and e to the x. I'm going to differentiate the line because it just becomes 2, gets easier. And I'm going to integrate the e to the x because integrating e to the x is just e to the x. It stays the same. It doesn't get any worse. It doesn't get any better. F prime is equal to 2 and g is equal to e to the x. So far, this is exactly what we would do if it was an indefinite integral, if the 0 and the ln 2 weren't there. So now you would go f times g, so f times g, which actually is the same here, f times g minus the integral of the two things I made, so 2 and e to the x. Okay, so that looks like I just totally ignored the 0 and the ln 2. I totally ignored the a and the b, the endpoints for a definite integral. Yeah, I did. Now I'm going to consider them. We keep them on this on the integral here. So they stay the same. But what about this f and g here? Well, what it gets is we need to evaluate this piece. So I'm going to put some brackets. Like blank and a line. So the integral turns into a straight line with the endpoints. The endpoint of ln 2 and the endpoint of 0. So we did our integration by parts, and we're keeping our 0s and ln 2s here. And now let's finish up with this here. This means on this side, sub in the ln 2 for x minus sub in the 0 for x. So it's like we already integrated, and we did. Remember from the integration by parts 1 video, this was just p prime that we integrated. So it's sub in the ln 2 for x, so that's 2 ln 2 minus ln 4 minus, when I sub in the 0 for x, that's going to be 0 minus ln 4. So I've taken care of this piece here. Now I have to minus this integral. So let's just work inside this bracket. If I integrate 2 to the x, I get 2 to the x. If I integrate 2e to the x, I get 2e to the x. But now it's going to be sub in the top, so for x, so sub in ln 2 minus sub in 0. E to the 0 is 1, so that's just 2. So now this was a definite integral, and we got a definite number. We can clean this number up, simplify some things down, but right now we've done the what about definite integrals question. We've addressed that. Let's do some cleaning up here. Things to note. 2 ln 2, I can bring this 2 in as an exponent, so that would be the ln of 4, and ln of 4 minus ln of 4 cancel. So these pieces cancel to be a 0. Minus a minus ln 4 is just a ln 4. All of this stuff cancels to be ln 4. E to the ln 2 is just a 2. E to the ln something is just a something. E and ln are inverse functions. So this is 4 minus 2 is 2. So the whole thing, I get a definite number, and the definite number I get is ln 4 minus 2. So the next thing we're going to talk about reduction formulas. I'm asking you here if you remembered the x squared e to the x case, and we even did another one that was, here, the x squared e to the x. We dropped it down by 1. It went from x squared e to the x to x e to the x, and then we did parts on that again, and it turned into x to the 0. So it went from x to the 2, x to the 1, and x to the 0 after we did parts on that. So we reduced the power by 1. That's what I'm thinking about here. So I'm going to think of this x to the power of n e to the x, and I'm going to do integration by parts on this where n is an integer, a positive integer. So I need a piece to differentiate, and the piece that I'm going to differentiate is that x to the n. That's what we did last time, but it was, the n was 2. And I'm going to integrate the e to the x. All right. So I'm differentiating. So the n comes down. Subtract 1 from the exponent, so n minus 1. I'm integrating the e to the x. That's just e to the x. So integration by parts is going to equal to f times g minus the integral of the two things I made. This f prime and this g are the two things I made. The integral of f prime and g. So there, I did integration by parts, and I reduced it by 1. I can take this n. N's a constant. I can take this n outside. So this is I've built a reduction formula. My original integral was x to the n. My new integral is x to the n minus 1. It should have gotten, one step simpler. So we've got our reduction formula. Let's do this. I got this example here at the end, but let's skip down to here and solve this formula. Solve this, which I would have to do integration by part. Nope. Let's do another example in here. So let's make n equal to 4. Now I could do integration by parts once, knock it down to x cubed, twice, knock it down to x squared, 3 times, knock it down to x, 4 times to knock it down to just e to the x. But with my reduction formula, I'm going to use this reduction formula each time. So the first step, n is equal to 4. So I'm just writing down my reduction formula here, but n is equal to 4. So that makes this 4 to the n, 4 minus 1 is 3. There. So integration by parts is built into that reduction formula. Now I need to do this integration. But in this integration, n is equal to 3. So I'm going to take this piece, I'm going to put my reduction formula in here, but everywhere there's an n, I'm going to put a 3. So that's going to be cubed 3. 3 minus 1 is 2. My new integral problem then is here, and that's just, I'm going to use my reduction formula again, but I'm going to use the reduction formula again here where n is equal to 2. So I'm going to copy this, paste it into here. Notice I'm careful with my brackets, and n is equal to 2. 2 minus 1 is 1, just x to the 1. Okay, now I'm going to do this integral, careful with my brackets, they're all nested. This integral, I'm going to use the same reduction formula, but n is equal to 1. So that's going to be x to the 1, so I won't write it. 1 minus 1 is 0, so this disappears. And, oh, this last thing here is just integrate e to the x. I can integrate e to the x, it's just e to the x. Now I'm done my integration. You can see that this formula with n equal 1, nested in n equal 2, nested with n equal 3, nested with n equal 4, plus c. And I guess I'm done. You could multiply this all out if you want to. I'm just going to leave it like that because it has the structure. But that's the idea of using a reduction formula that we built once to do the integral. Here's another idea then with cos to the power of n. We're going to develop a reduction formula and use it to integrate this cos to the n. All right, let's make our reduction formula. What are the two parts? Oh, okay. What are the two parts? We're going to have to have one of the parts be a cosine, and the other be the one of the cosines, and then the other to be the rest of the cosines. So one of them is cosine x. That's one part, and cosine x to the n minus 1. That's the other. Those are the other parts. And remember that cosine x to the n minus 1, that's like cosine to the power of, I'm going to think of it like this because it makes it makes it easier to think about rather than this notation. So I need one piece to integrate and one piece to differentiate. The piece I'm going to differentiate is the more complicated piece. The piece I'm going to integrate is just the cosine x. Okay. Differentiate. The n minus 1 comes down. Subtract 1 from the exponent. So I'm doing chain rule. So it's n minus 1 minus 1, or minus 2. Leave the middle alone, and now I need to multiply by the derivative of what's inside. The derivative of cosine is minus sine. So all of that is just the derivative of cosine x to the power of n minus 1. Now let's integrate cosine. That's sine x. Differentiate sine, get cosine. Okay. So now we're going to build our reduction formula. It equals f times g. So f times g. This is f. F times g minus the integral of the two things I made. So integrate, I made these two bottom pieces here. So I've got this and times g dx. So now we're not done yet with our reduction formula. We can make things a little bit simpler. First thing I can see is that this n minus 1 is a constant, so let's bring it outside. Sine times sine, I'm going to write that as sine squared. This minus sign, let's bring this minus sign to the outside and make that a plus. So we're trying to make everything a little bit simpler. Now, I have a sine squared here. It's going to be nice if I make this sine squared. I'm going to use the grandfather Pythagorean trigonometric identity. Sine squared plus cos squared equals 1. So sine squared is equal to 1 minus cos squared. Why is that better? Well, let's multiply this through across this minus sign. Okay. So the integral I want equals I is equal to if I multiply across this, so I'm just cleaning this up here, put this in a bracket. I could make that as this piece dx minus integrate Okay, so I'm distributing this cos x to the n minus 2 across this bracket. This minus sign is this minus sign. But here, cos x to the n minus 2 and n squared, these clean up to be just straight cos to the n if I add exponents. So, and this is my original integral. So I can do the same thing, the same trick that we did with that e to the x sine x. I can solve this for I. So let's see what we got. We got I equals this whole piece here. I'm distributing this n minus 1 across this bracket. So that'll be also times n minus 1. And when I bring this over to the other side, it's going to be a plus n minus 1 times I. Okay, so then I times this, if I expand this all out, that's going to be n times I is equal to just this. I'm almost done, because now what I want is I equals, right? So let's divide everything by n. There's my I equals, and okay, I is this. So this is our reduction formula. And notice it reduces the power n down to n minus 2. It knocks it down powers of 2. So then this, if I'm going to use this reduction formula, repeat it over and over and over again, this is either going to end, if n is even, this will end eventually at a cosine squared, and then I do it again, and I guess it would be a 1. Or if n is odd, then this would eventually end to be just cosine, and I can integrate cosine, sine. So this ends either way. Let's use this reduction formula to solve this to the power of odd 1. Okay, so now I'm going to use this rule when n is equal to 7. So I'm going to use this rule when n is equal to 7, Control C. N is equal to 7, so that's going to be a 7. 7 minus 1, that's to the power of 6. 6 over 7. And to the power of 5. So I used the reduction formula. So these reduction formulas are making our integration a lot easier, but in some following videos, the trig integration videos, we'll be able to do this cosine to the 7 even easier than the way I'm doing it now. So what am I doing next? I've got this, and I want to do this integration here. So but I'm going to use in this integration, I'm going to use my reduction formula, but n is equal to 5. All right, I think I need more space here. So I'm working with my reduction formula here, but everywhere there's an n, I'm putting an n is equal to 5. So that's going to be 5. 5 minus 1 is a 4. 4 over 5. And 5 minus 2 is a 3. Okay. So now I'm working with this integral. Put it in brackets. I'm working with this integral where n is equal to 3. So 3 minus 1 is 2. 2 over 3. And 3 minus, that's just cosine now. Okay, the only integral left here, oh, I made n is equal to 3 here. So the only integral left here is integrate cosine, which is just sine. So I'm replacing this whole thing here with sine x. Almost done. Plus c. Now I'm done. So we did our reduction. Oh, and you could, expand out these brackets if you want to clean this up. I'm just going to leave it, but you could multiply it all out if you wanted to. So this is the idea of using a reduction formula. Once we built it, it makes some of these like trig to a power easier to use, just like we did on this example here with the x to the 4 e to the x. Oh, okay, that one was a long example. I look over here, we got 3 more examples. Yeah, but these ones aren't as long. So let's finish this off. This next one, and every one of these examples has a point to it. The point to this one, this isn't cosine times ln, it's ln is inside the cosine. So it's not integration by parts yet, but it will be. The first step I should make is a u substitution. Let u equal ln of x. Substitution is at least a 2-part process, so I differentiate my substitution. Du dx is equal to 1 over x, and that means that dx is equal to, when I solve for dx, x du. Okay, so let's put those pieces in. That's going to be integrate cosine of u, and in place of cosine, or sorry, in place of dx, I'm writing x du. And this x is not inside the cosine, it's on the outside. All right, now I'm almost, well, okay, I wish this x wasn't there, right? I'm trying to write everything in terms of u, and so that I can integrate with respect to u, but I still have this x left over. I need to replace this x as some function of u. If u is equal to ln x, then x is equal to e to the u. So after I do this substitution, now my new problem is integrate e to the u cos u du. This we can do. I'm going to leave this for you to work out, but it's the exact same structure as we did way up here, e to the x sine x. You're going to end up doing integration by parts twice. It's going to look like you're going around in circles, but you're going to make that integral equal to I. After you solve this, you'll end up with some formula that looks very close to this. Where were we? That looks very, I lost my spot here. That looks very close to here. It looks very close to this formula that we got, but it's just with a minus sign. But then that's going to be in terms of u. So everywhere there's a u, you're going to need to put back in for ln x. So you'll have, cosines and sines of ln x. And then don't forget a plus c. So I'm going to let you finish that one. The point here was we could do a substitution and then it turns into integration by parts. Next example, because I promise these ones will be quick. I want to integrate arc sine. I know how to differentiate arc sine, but I don't know how to integrate it. Oh, so that's one of those cases where we'll throw a 1 in front so that I have two parts. We have a piece to differentiate, that's the arc sine, and I have a piece to integrate, that's the 1. When I differentiate arc sine, 1 over square root of 1 minus x squared. And when I integrate 1, I get x. So now we can plug this in as the two pieces. F times g, so x arc sine x minus the integral of the two things I made. All right, but this is a definite integral. So I need to evaluate this at the end points. So from a half from 0 to a half, and likewise these endpoints should be on here, a half and 0. Okay, what's left to do? Sub in the 0 and a half here, also evaluate this integral, and then sub in the points. So let's do first things first. When I sub the half in, that's going to be a half times the arc sine of a half. Minus 0 arc sine is 0, that's just 0. So there's subbing in the top minus subbing in the bottom for that. Arc sine of a half, we'll work that out in a minute. Now, can I do this integration? Yes, this integration I can do if I let u equal to 1 minus x squared, then a multiple of the derivative of what I'm letting u is on the top. So now I'm just working with this piece here. That means that, okay, substitution is at least a two-part process. So du dx is equal to minus 2x which means that dx is equal to du divided by minus 2x. This is why it's going to work, is because this x is on the top. So I'm replacing this dx with du divided by minus 2x. I'm replacing underneath that square root sign with a u. This x and this x are going to cancel. And this minus a half can go all the way to the outside. In fact, I'm just going to work inside that square bracket right now. So let's just put that outside like that. Okay. Here's something we hadn't seen yet. When we're doing definite integrals, that's 0, that's an x equals 0, not a u equals 0. This half, that's an x equals. So I need to switch over the endpoints as well. So when x is equal to 0, u is equal to 1. So I'm going to switch over everything to u's. I'm going to switch the endpoints. When x is equal to a half, u is equal to, plug it in the formula here, a half squared is a quarter, 1 minus a quarter is 3/4. So I'm switching over everything to u's. So this why do that? Well, now when I do this integration, I don't have to change back into x's and then sub in the 0 and a half. I can just integrate with respect to u's, and that's a u equals 1 and u equals 3/4. I can just sub in the top minus sub in the bottom. I don't have to switch back. It's a better way to do this. So I'm just worried about this piece here now. Let's okay. When I integrate, when I'm thinking of this is just u to the power of minus a half. I'm going to think about it like that because it's going to make it easier to integrate. It's going to be an add 1 to the exponent, so that's going to be u to the half, divide by what's up top. So this is me integrating. That's the integral of 1 over square root of u, or u to the minus 1/2. And I still have to go sub in the top, minus sub in the bottom for this piece here. Let's cancel this 2 and this 2 and just make that a minus. I still have to sub in the top minus sub in the bottom for u's. So let's do that. I still have all of this. I'm not going to write minus 0 anymore. When I sub in, that's going to be 3/4. The square root of 3/4 is root 3 over 2. Sub in the top, minus sub in the bottom, minus a minus is a plus, square root of 1 is 1. Okay, there, sub in the top. Now, all that's left to do, not a plus c, because it's a definite integral. The arc sine of a half, the sine of what angle is a half? The sine of 30 degrees, or better, pi over 6. So the sine of arcs, or the arc sine of a half, is pi over 6. And then I can make this pi over 12 by multiplying by the half. Well, let's just leave it. Get our number. Oh man, one more example. And that's it. Okay, And this example is going to be super straightforward because by this point we know what we're doing. I'm going to do integration by parts. I need one piece to differentiate and I need one piece to integrate. The e to the x cubed looks like that should be the piece that I integrate, but I know I need an x squared tacked on the outside to make my integration easier. So that means that I should differentiate the x cubed. When I differentiate the x cubed, I get 3x squared. And when I integrate the g, I'm getting this e to the x cubed, so times a third. Where does the third come from? If I were to differentiate this, I would get e to the x cubed times 3x squared. The 3x squared, I just want it to be x squared, so that's where the 3 is. So integration by parts equals f times g. Let's put that on top. F times g minus the integral of the two things I made. So the 3x squared and the 1/3, this 3 and this 3 are going to cancel. So I'm just going to be integrating x squared times e to the x cubed. And this integral I can do. So let's clean this up. Let's finish this. Integrating x squared e to the x cubed is 1/3. Done. No, plus c. Done. Okay, integration by parts. A lot of things to practice, but it is, except for u substitution, it is the most important technique that we've learned so far, and probably the most important technique for the remainder of the course. And if you take differential equations or some kind of econometrics or business finance math, integration by parts shows up a lot all over the place.